Alright, looks like I'm playing Desert Bus. For those of you who don't know, Desert Bus was part of a minigame collection from Penn and Teller's Smoke and Mirrors. The game was developed for the Sega CD, and the whole thing was a joke, literally set to release on April Fool's Day, though it never actually hit the market. What do I mean the game was a joke? Well, the game consists of driving a bus along a straight road from Tucson, Arizona to Las Vegas. With a top speed of 45 miles an hour and the route being 360 miles, it takes 8 real life hours to make one way trip. The only other mechanic is that the bus veers to the right, requiring the player to regularly steer to the left. If there's any game that would benefit from being automated, it would be this one. So you can just let it run by itself and not waste your time playing it. To get started, I needed some version of the game to play since the original was never released. Doing some research, it seems like there were a handful of options, including numerous options on Steam, but the version I decided to go with was Road Trip by SAC on itch.io, since it was so easy to start running and seemed to be one of the most faithful adaptations. Other incarnations seemed to add actual gameplay mechanics, but SAC kept it true to the original, mostly just adding an interactable radio. Real quick, I'd like to give a shout out to Sack for developing the game, and I'll link to his itch.io dev page in the description. Before I started coding, I figured I'd actually go ahead and try the game for myself. Whee! Okay, it was a little more fun than I thought, but I definitely couldn't do it for 8 hours. Looking at the instructions and playing the game, we need to be holding W to move forward, and when we're moving forward, we always drift to the right. A steers us to the left, and D steers us to the right. Steering to the right appears to be faster than steering left. Seemingly, the natural drift and steering are both added to our horizontal velocity. Not that I played for long enough for you to see it, but the game also has a day and night cycle, which might be relevant to the solutions we can use. As I was playing, I was starting to brainstorm ways to approach this problem. And while doing so, I wanted to embody a philosophical principle called Occam's razor. Occam's razor dictates that the simplest solution is usually the best. I'm a big believer of this idea, partially because it means you don't have to think about complex solutions. But combining this idea with my gameplay experience, I realized you could probably just get the computer to win by pressing left on a set timer. I need a couple of things that I'll import from other modules. I need a way to have key presses register, which I can get from PyDirect input. It also conveniently provides a clicking method, which helps make sure we have the correct screen active. I likely could have used PyAutoGUI for this as well, but following CodeNoodle's suggestion, I didn't think that module would successfully key press for Bowser's Inside Story, so now I'm just using PyDirect input for key presses out of habit. I also need to have some code that waits, which is a super common module and method, time.sleep. I added some code to click into the correct window, and then the forward key should be held down the entire time the code runs. Then I added a while true loop that would press the left key and pause for a given amount of time, starting at 1 second. Let's see how it runs. While the code is running and trying to do the right thing, you can see that we're still drifting pretty hard to the right, losing in a matter of seconds. In that case, it means we're waiting too long between button pushes, since we move to the right much faster than we move left. In theory, we should be able to narrow down this window to a perfect time, but how do we find it? Well, this could be done using a core algorithm in computer science, binary search. Binary search is the process of splitting your remaining search space in half to greatly reduce the time and cycles it takes to arrive at the outcome you're searching for. I'll link a couple of videos that also explain this, but I want to go on a tangent and explain it myself here. A classic example used for this is the game Guess Who. The optimal strategy for Guess Who involves splitting the remaining groups into two equal halves to the best of your ability. To highlight just how much more efficient it can be, I'm going to seriously exaggerate it. Imagine you're playing Guess Who with a computer database that has all the info of every person alive, which I'm going to just go ahead and call 8 billion people. Let's pick between two strategies, just guessing one person at a time, or instead asking a question that can split the remaining people into two even categories. We'll assume such a question exists at every round for the sake of the example. Let's now say each question takes 1 second for the computer to answer. For the first approach, on average, it will take 4 billion guesses to get the right person. While sometimes you could get it on your first guess, other times you might need to take 8 billion guesses, so we'll go ahead and go with the average of 4 billion. For binary search, it'll always take the same number of questions, since we're eliminating half the population with every question. To figure out how many questions that is, we can do some simple math. We'll need to divide 8 billion by 2, then that result by 2, and so on until we only have one person left. Since dividing is the same as multiplying by a fraction, we can multiply 8 billion by 1/2. We also need to do this multiplication repeatedly. Repeated multiplication is represented by exponents, but since we're looking for how many times it takes, we'll go ahead and make that exponent a variable. And since we're going to do this until we reach one person, let's set it equal to 1. Then we do some division, some log rules, some more division. We find that x is approximately 32.9, and since we can't make a partial guess or question, let's just go ahead and call it 33 questions. So it's 4 billion versus 33 questions. At one guess a second, that's a difference of 33 seconds versus almost 127 years. The oldest person to ever live, Jeanne Calment, lived to 122 years old. She could have started asking questions from the day she was born till the day she died, and still would have needed 4 years to take the average number of guesses. If you assume that the questions we ask to split the database in exactly half took a year to come up with and process in the database, you would still expect to finish almost a century earlier than if you guessed one at a time. That's how fast binary search is. What was I supposed to be talking about again? Oh yeah, Desert Bus. Since I started my sleep time at 1 second and we drifted right, that means I'll need to lower the amount of time paused between key presses. First, I'll remove the pause entirely to ensure that we can do this at all. If we still drift to the right, something is wrong. Great, we're drifting way left. That means the ideal time is somewhere between 0 seconds and 1 seconds, so my next guess is 0.5 seconds, the value halfway between 0 and 1. I'll speed through the next couple trials. At 0.5 seconds, we're drifting to the right, so we change the value to 0.25 seconds. At 0.25 seconds, we're still drifting to the right, but at a much slower rate than before. Dropping to 0.125 seconds, we drift left, so that means we need the value in between 0.125 and 0.25, so we go to 0.19 seconds, rounded up. The problem with this approach, in this context specifically, is the closer I get to the correct value, the longer it takes to verify if we're drifting off road and in which direction. I skipped over several iterations I tested to show you the closest time I found, 0.20125 seconds, and while it looks straight, in my personal testing, even this eventually drifts off road. Theoretically, using binary search would eventually work, and likely sooner rather than later. However, it would be hard for me to trust that the sleep time I found using this method would work without letting the car run the whole length of the road, and that would be way more trouble than it was worth. I don't even want my laptop running that long. The battery's already fried. I had the thought that I could mess around with the other timing variables, such as how long the key was held for, but after a second I realized that it doesn't do anything other than violate the principle of Occam's razor. I would still have the problem of measuring the timing, I would just have to juggle multiple timers. I tried finding the source code of the game. I was hopeful I would be able to find the exact rate you move when holding versus not holding the button, and use that to carefully measure out how often or long I should push left for. However, there weren't any GitHub links, and I couldn't find anything upon doing an inspect element. I was going to reach out to Zach to ask, but his last post on itch.io was over 112 days ago, and I didn't feel like waiting that long to get this working. So I decided to move on to a different approach. Does that mean I wrote a 2-minute long rant about the importance of binary search and its effectiveness, only to not end up using it in my final solution? Yes. But it is an important concept that I wanted to cover. And it still saved me a lot of time, since it reduced how long it took me to realize I needed to change my approach. So, what now? I decided it was time to actually start getting values from the screen. But it's going to look pretty different from what I've been doing for Bowser's Inside Story. There's not really a good image to target, and where I take a picture might change as the car moves. Then I realized I could do something similar to a real life drive, and just make sure I stay inside the white edge line on the right. To do that, I busted out my friend PyAutoGUI, which has a handful of tools to help us out. It has a method, position, which gives us the XY pixel position of our pointer's current location. This in and of itself never got used in the code that's the solution, but it helps me get some relevant data in conjunction with the next method, pixel. Pixel takes an x and y coordinate and returns the color value in an RGB tuple format. I realized that by placing the mouse right in front of the truck just left of the white line, I should be able to detect when the mouse goes over the white, in which case I need to press left. Normally, I would just start writing code and fix issues as they pop up, but this time I did the unthinkable and actually anticipated some of the problems before they arose. Before I started running the new program, I did some research using position and pixel. First, I got the exact coordinate I wanted the mouse to click into the screen. I then also started checking the pixel colors of the road asphalt and the white lines. I was originally anticipating just checking whether the color value was above some value that would be true for the edgeline and not the road, but with the day and night cycle, the edgeline at night is actually darker than the road during the day. The edgeline is still darker than the road at night, so I can simply just check the color on each loop, and if it noticeably got brighter than the previous loop, I'd press left. And that's really all there is to it. I'll note, the road on the original Desert Bus doesn't have any edge lines, so you'd likely need to adjust this slightly. But other than that, there isn't much else to say. I'm also not going to leave my recording running for 8 hours to prove that it would make it all the way. If you're inclined, feel free to download from my GitHub and let it run to your heart's content. Also, during my research of the game, I found an event called Desert Bus for Hope, and I feel like I should go ahead and shout them out here as well. Desert Bus for Hope is an annual charity event that plays Desert Bus as long as people keep donating. The money goes to Child's Play, a charity that provides video games, toys, and books to hospitals all over the world. I strongly recommend checking them out. Links for both in the description. I'm pretty sure this year the stream's going to be on October 23rd. Again, shout out to Slack for making this version of the game, and feel free to suggest other games in the comments. Until next time.